Hello and welcome to this AQA Further Maths Statistics video, starting to look at continuous random variables. From A-level maths you should be familiar with the fact that some variables are continuous. Variables in a population such as height or weight are continuous variables that can be modelled by a normal distribution that takes this bell-shaped symmetrical shape. You should also be aware that the mean, which is indicated here with the red line, is also the mode and the median and is denoted by the Greek letter mu, and that normal distributions are also defined by the measure of spread of the distribution, and that's denoted with the Greek letter sigma. The way we describe by writing down the fact that a random variable that's continuous, x, follows a normal distribution is to write it in this way, and following the n telling us it's normally distributed, we have two numbers. The first one is the mean mu, and the second one, just make note, is not the standard deviation but the standard deviation squared, or the variance of that particular distribution. And you should also be aware of the fact that if we go one standard deviation above and one standard deviation below the mean, the percentage of the population between those two values is always, for any normal distribution, around 68%. And if we go two standard deviations below and above, we capture about 95% of the population. And once we get as extreme as 3 standard deviations above and below, we've virtually captured the entire range of outcomes possible for that distribution. So this is a curve that is an example of a probability density function, and for continuous random variables we denote this function by calling it fx. And for the normal distribution this function is very complicated, and you'll notice that it involves our parameters mu, the mean, and sigma, the standard deviation. And if you have a graphics calculator, you might just like to play around with that particular function and change the values of mu and sigma and see what curves you can draw. If we want to work with this curve, say we've got a distribution and we may want to find the probability, for example, of an outcome being between the values of 11 and 12, that's exactly equivalent to working out the area under the curve between the values 11 and 12. In terms of doing this at A level, obviously this function is too complicated to integrate, so in practical terms you will be using a calculator or tables to evaluate such probabilities. So if we look at an example, our random variable here, x, represents the height of a pupil, and that continuous random variable is normally distributed with mean 135, and remember the second quantity in the brackets is the variance, so 225, the standard deviation squared. And we want the probability that a pupil chosen at random is greater than 118, so the probability x, the height, is greater than 118, and it's worth noting that that is exactly equivalent to the probability that x is greater than or equal to 118, and that's very different to the situation that you encountered when you looked at discrete random variables. Those two probabilities would be different in that case. It's also worth noting that the probability, for example, that a student is exactly 118 centimeters tall would be 0 in the context of a continuous random variable, and that's because 118 is simply one possible outcome from an infinite number of outcomes for a continuous distribution. So if we look at using the calculator to find such a probability, you'd need menu 7 to get the distribution function, and you will always be using option 2, normal cumulative distribution. Option 1 is not relevant to what you're doing at A-level. It's an approximation to this sort of exact probability that I've already explained to you. The probability would be 0 in the case of a continuous random variable at A-level. You'll then be prompted to give the calculator the information, so standard deviation and mean, and then it requires upper and lower limits for the boundaries of your probability. Well, we want to be greater than 118. So looking at this little sketch here, we're fine putting in the lower limit of 118. What could we put in for the upper limit? Well, just recall that if we look at a population, a normal population, if we go 3 standard deviations below and above the mean, we've virtually got the whole population there. And therefore you just need to choose a value, and I chose 200, that's more than 3 standard deviations above the mean. And then that will give us the probability required. And the answer is just given to you directly. And it's worthwhile, just with your sketch, thinking what sort of size probability am I expecting? A 0.871 is perfectly reasonable because we have a very large probability here, and bearing in mind that the whole area under the curve will equal 1 because it's the sum of all the probabilities of all the outcomes you can have for that distribution, 0.871 is a perfectly reasonable answer. If we now just recap on the standard normal variable that's denoted Z and is normally distributed with mean 0 and standard deviation and variance both equal to 1, we need to be able to use this to solve problems sometimes involving the normal distribution at A-level. And so you need to be aware of the transformation from our real life reading variable to our standardized reading or variable. And Z is obtained by taking the real life variable and subtracting the mean, so we find out how far above or below the mean we are, and dividing by the standard deviation. And that means that in effect a Z-score is simply telling us how many standard deviations above or below the mean a particular outcome is for a particular distribution. And you can probably look into your A-level textbook a bit more and just look into this if you want to do a bit of revision. And there's a very nice little activity that you can follow this link to on GeoGebra that will enable you to come up with a real life situation, an X value, and that's shown in pink, and work out some probabilities. And you can see the areas sketched and the curve sketched for both the real life situation, and you can see in blue on the left there the standardized values, and you can see how although the areas look different, actually the probabilities are equivalent to each other. And that's the end of this video.